Today, let us see how to read closed loop frequency domain specifications by using open loop response by superimposing this open loop frequency response on a Nichols chart that we will see today. So, by using this Nichols chart, we can get the closed loop frequency domain specifications from open loop response. That is the advantage of Nichols chart. Find the phase margin, gain margin, bandwidth, resonant peak by using the Nichols chart for the system whose open loop transfer function is G of S equal to K multiplied by e power minus 0.1 S upon S multiplied by 1 plus 0.1 S plus 1 plus S. This is the given open loop transfer function. This is the open loop transfer function. Here you notice that G of j omega equal to e power k multiplied by e power minus 0.1 j omega upon j omega 1 plus 0.1 j omega 1 plus j omega. This is sinusoidal transfer function. We have to assume k equal to 1. We assume k equal to 1. This is the sinusoidal transfer function. The magnitude of this is always equal to 1. Its phase is changing, angle is changing as omega varies, So this is a delay function. Phase shift function. Delay function or phase shift alone function. So it will not come in the magnitude. While finding magnitude, modulus of j of j omega, this will not come into picture. It's 1. Therefore, the magnitude is 1 upon omega square root of 1 plus 0.01 omega square root of 1 plus omega square. That is magnitude. If you vary omega, you will get different values that is tabulated here. From omega equal to 0.1 to 100, it is plotted here. For 0.1, the magnitude is 19.96. For 100, it is minus 80 dB. It is in dB scale. To convert this into dB scale, we have to multiply this by 20 log modulus of g of j omega. You have to find. That is equal to minus 20 log omega plus 20 log minus 20 log square root of 1 plus 0.01 omega square minus 20 log square root of 1 plus omega square. If you vary omega, you will get a table of values in dB. Then we have to find the angle. While finding angle, this will come into picture. What is that angle of G of j omega equal to? This will be 0.1 omega minus 0.1 omega. But this is in radians, but we want in degrees. That's why multiply this by 180 divided by pi. Then minus, for this, this minus 90 degree, minus tan inverse of 0.1 omega, minus tan inverse of omega. So if you vary omega, as we did for magnitude 0.1 to 100, you will get angles varies from minus 96.85. Now we are going to find the closed loop frequency domain specification from open loop response. That is the advantage of Nichols chart. So we have to plot this on Nichols chart. This is the Nichols chart. Nichols chart. In this Nichols chart, we have to draw this open loop response. Here, the x-axis is in degrees and y-axis in dB. Here, in the same scale, this M circle and M circles, M circle and N circles are plotted. Here you can see that the M circles are plotted in decibel scale. It is symmetrical about 180 degree. That's why it is in the middle. It is symmetrical about 180 degree, that you can notice. The 0 dB of Nichols chart and our open loop response are coincides here, and 180 also coincides. 180 also coincides. That way, the Nichols chart is superimposed on this graph sheet. Like that, you have to assume. Here, this is the block line, and the black line is the response, open loop response, plotted on this superimposed sheet. This plot is called a Nichols plot. After drawing this on this Nichols chart, so once it is drawn on this here, notice that omega has no meaning. It is plotted between the phase shift and phase angle and magnitude. That's all. But you can notice that as omega increases, the magnitude drastically decreases and the angle increases in negative direction. That's all. Magnitude decreases and the angle increases in the negative direction, that you can notice. Once you plotted, now we have to read the closed loop frequency domain specification. It is note that this is tangent to 3 dB circle. This is tangent to this 3 dB circle, 3 dB M circle. Therefore, the resonant peak, closed loop resonant peak is equal to 3 dB. The frequency at which this occurs, how to find that? We have to mark this point. We have to mark this point. We have to mark this point, the tangent point B. What is the coordinate for this point? We have to see. The coordinate of this point is minus 0.4 dB, comma 0.823 radians. Therefore, resonant frequency equal to 0.823. 0.823. So we read two closed loop values. One is resonant peak and the resonant frequency at closed loop we read. Next, what we have to read? Resonant peak. Then bandwidth we have to read. The bandwidth. How to read bandwidth? We have to find the bandwidth. We have to consider the minus 3 dB M circle. Minus 3 dB M circle. This is the minus 3 dB M circle. In decibel scale, it intersects at C. It intersects the plot at C. At this, the coordinates are C, that is minus 3 dB intersection. Minus 3 dB intersection, the coordinates are, if you read coordinates of this, what you are getting is minus 6.6 dB, minus 6.6 dB, and the frequency is 1.32 radians per second. Once you got a magnitude, you can read this from the table, 1.32 radians per second. Or once you read the frequency, you can get the magnitude from the table by interpolation. So minus 6.6 dB. Therefore, the bandwidth equal to 0 to 1.32 radians per second. So we have to find the frequency at which the minus 3 dB M circle cuts. That's all. That is bandwidth. Now we have to find the gain margin and phase margin. To find the gain margin and phase margin, draw a vertical line at 180. Draw a vertical line at 180. It cuts the magnitude plot at A. At A, what is the magnitude we have to see? What is the magnitude we have to see? The magnitude at minus 180 equal to minus 14.3. Therefore, gain margin equal to minus of minus 14.3 equal to 14.3 dB. That is gain margin. How to read the phase margin? Draw a horizontal line at 0 dB. It cuts here at the same, say, D, at D, project vertically, you get the angle minus 135. Therefore, phase margin equal to 180 plus 5, that is equal to 180 minus 135 equal to 45 degree. 137. Therefore, 43 degree. Phase margin equal to 43 degree. That's all. So let us review what we have to do. We have to obtain the open loop response for the given open loop transfer function. Plot this on Nichols chart. You will get Nichols plot. Then find the M circle which is tangent to this magnitude plot. This is here. It is tangent to 3 dB M circle. Therefore, resonant peak is 3 dB. At that point, at tangent, we have to find the coordinates, that is minus 0.4 dB open loop magnitude, and frequency is 0.823. Therefore, resonant peak at closed loop is 0.823. Now we have to find the bandwidth. To find the bandwidth, we have to consider that minus 3 dB M circle, where it intersects the given open loop response. We have to find it intersect at the magnitude of 0.66 and frequency of 1.32 radians per second. Therefore, the bandwidth is 0 to 1.32 radians per second, or bandwidth simply 1.32 radians per second. To find the gain margin, draw a vertical line at 180 degree phase shift. It cuts at A. At that point, the magnitude is minus 14.3. Therefore, gain margin equal to minus of minus 14.3 dB. That is 14.3 dB. That is gain margin. To find phase margin, draw a vertical line at 0 dB. It cuts at D. Draw a vertical line. The angle is minus 137. Therefore, phase margin equal to 180 plus 5. That is 180 minus 137. That is 43 degree. That's all. This way, we have to read the closed loop specifications, frequency domain specification from Nichols plot.